In the last lecture, we talked at some length about sensory and working memory. Now, we focused a lot on working memory as the place where all of the operations that our mind performs occur. It's the workbench of the mind. It's where we do all of the work that our minds need to do on the information that's presented to us. So what kinds of processes are actually going on in our working memory? Like when we hear words, each word representation has to be combined to make like a sentence representation, right? That's what's going on right now. You're hearing words that I'm saying, you have to combine them into a sentence. So we do constructive operations like building a sentence representation. We do transformations of information, right? Like mental rotation. Take a mental image and we can rotate it in our mind. We can scan and zoom through our mental images. We can also do decision processes like identifying something or performing a comparison or deciding on a course of action. All of these things are things that happen in our working memory. But I want to focus on one operation in particular. I want to focus on search. So let's suppose some new information has just entered your working memory. Now you need to find that one piece of information in the workspace. You can think of this like an actual workbench. You've got a desk and it's cluttered with stuff. Oh, new stuff's always coming in. Well, wait, where was that paper? Where did I put it? Oh, that was the one that I need. Where did it go? I have to do some kind of search. I need to find it in the midst of all this other information. So how does this work? How can we accomplish this? How do we actually execute search? What we need is an algorithm, right? Think about those levels of analysis. We need an algorithm that describes how we can search through all the information in our working memory to find the thing we are looking for. What is the specific sequence of steps that we can undertake in our working memory to find a piece of information? How do we search? I'm going to show you a series of numbers, one at a time. Then I'm going to ask you if you saw a particular number. We refer to that as a probe. I'm going to give you a probe to see if you saw a certain particular number. Okay, are you ready? Did you see a 3 somewhere in that sequence of numbers? That probably wasn't very hard to answer, was it? Yeah, I saw a 3. So what? Well, how do you know that there was a 3 there? What exactly was the mental process that led to you being able to say, yes, I saw a 3? You have to do some kind of search, right? All of those numbers go into your working memory, and then you have to be able to scan through all of that in your working memory, find a 3, and then say, yes, I did in fact see a 3. So there's some kind of process happening here that involves searching. We can consider a few different kinds of search algorithms, right? So now you have a mental representation of the numbers that you just saw in your head. You saw all the numbers one by one. All of that information is going into your working memory. So now you have a mental representation of all those numbers that you just saw. And what you need to do is you need to find the number 3. The question is, how can we actually do this? We can consider a couple different algorithms that can accomplish this task. Let's think about algorithm number 1. We put the numbers in a row, line them all up. Then what we do is we're going to start with the first number and just ask, is it a 3? If it is, then wow, great. Well, we already answered the question. We know that there's a 3 present. If not, we got to keep moving until we find a 3. So this is a pretty simple algorithm. We're just going to line up the numbers and then we're going to go one at a time and scan each one by one until we find a 3. Easy. Maybe there's a more efficient way of doing this though. Let's think about algorithm number 2. Maybe instead of checking each number one at a time, maybe we can just check all the numbers all at once, right? Like maybe we can represent them visually and then just look at the image all at the same time and see if we can find the number. Why do we have to scan them one by one? Maybe we can check all the numbers at the same time. It would be a lot easier. It's only one step. What's the difference between these two algorithms? The difference is the difference between serial and parallel processing. Algorithm number 1 is serial. There are several consecutive steps. You have to line up the numbers and then you scan them one at a time. Each of those scanning operations is a new step in the algorithm. Algorithm number 2 is a lot simpler, right? It's only one step because you're doing everything in parallel. You're looking at every item, but at the same time. So instead of being a whole bunch of consecutive steps, it's a one-step process. Step 1, scan numbers. Done. Oh, that's way easier. So when we think about memory search, we can think about the computational level. The goal of memory search is to find an item in a collection or a list or an array, or however we think it's organized in our working memory. So we can think about serial and parallel search as two different models, two different algorithms that can accomplish that same goal. It's two different ways of processing this information that can get to the same output. The output being that decision of whether you saw a 3 or not. And what's the difference between these two algorithms? What different predictions can we make from these algorithms? That's the real question. What we want to know is which of these algorithms our mind is actually using. So we need to think about this in a way where we can generate actual testable predictions. How can we observe whether our mind is doing one algorithm or the other? So let's imagine running each search algorithm over larger and larger sets of numbers. As the size of the set of numbers increases, how long is each search algorithm going to take? Will they take the same amount of time, or will it change? Well, let's think about algorithm number 1, the serial algorithm. And if we suppose that it takes time to perform each step, each operation, since they're happening consecutively, if each operation takes some amount of time, then that means that the more items there are in the set, the more things that you have to search through, the more steps you're going to have to take, and so the longer the search is going to take. The more numbers you introduce that you have to scan through, then the longer it's going to take you to search through that set to find the number you're looking for. I think that makes sense. That feels intuitively right. Sure. The more numbers there are, the longer it will take because you have to scan each one individually. Is that true for the parallel algorithm? If we're doing parallel processing, if we're scanning all the items simultaneously, we're only doing a single step. So it shouldn't really matter how many items there are. The search time shouldn't really change. At least not if we really are looking at all of them all at the same time. So that's a difference. And that leads us to a different prediction about something that we can actually observe. It leads us to a prediction about human behavior. This means that if we actually have people sit down and do this, if we show people lists of numbers and then ask them to recall if they saw a certain number, we should be able to figure out which algorithm they're using by looking at how long it takes them to answer the question. If we increase the set size and it takes them a lot longer, then that looks a lot like they're using a serial algorithm. If we increase the set size and it doesn't change how long it takes, then that looks a lot like parallel processing. Let's think about this another way. For our serial search algorithm, we're going to need to perform at least 2 steps. First step, we have to arrange the numbers in a row. The second step, we have to scan each number. And actually, this is going to be a lot of steps, right? Step 2 actually subdivides into a bunch of steps because you have to scan each number one at a time. So the question is, will we find the first number and the fourth number in the same amount of time? I think the answer to that is no, not if we're searching them in order, right? If we're looking at one number at a time, then the first number that we scan should be very quick, but the fourth number is going to take a little bit longer. It takes us longer to get to that step. Well, what about the parallel search algorithm? It's the same thing. We have to arrange the numbers in a row, but then we're going to scan all of the numbers at the same time. So in this case, will we find the first number and the fourth number in the same amount of time? I think that we would predict, yes, we should find them in the same amount of time. It shouldn't matter where they are in the list because we're looking at all of them all at the same time. So even if it does wind up taking longer for a larger set, maybe it just takes us longer to scan a really large image or whatever, even if we're scanning it all at the same time, it still won't matter whether the number we're looking for is first or fourth or 10th because we're looking at the whole thing all at once. But for our serial algorithm, it really matters whether it's first or fourth or 10th, because that's going to determine how many steps it takes to get to that number. And that's going to determine how long it takes to make the decision about whether or not you saw that number. So already we have two different predictions. If we're using serial search, then we should be able to modulate how long it takes to do this computation based on how large the set is, but also based on the position of the number in the set. For the parallel algorithm, this shouldn't be the case. We shouldn't see any modulation for how long it takes to do the computation based on position. We may not even see any modulation based on set length. You might remember serial and parallel processing from our lecture on visual perception, when we talked about the kinds of operations that are being done in the visual domain. Remember when we talked about this, we talked about feature integration theory. When two or more features differed, then we would use a serial algorithm. But when only one feature differed in the set, then we would use a parallel algorithm. So we already know that the mind uses serial and parallel algorithms in certain circumstances. Now the question is, in this circumstance, in this situation, the situation of performing a search in our working memory over an array of numbers, which algorithm do we use? Serial search or parallel search? We can summarize our predictions with these graphs. For serial search, as the size of the set increases, the search time will also increase. For parallel search, as the size of the set increases, the search time should remain flat. It shouldn't increase. It should take the same amount of time because we're only doing one step. This experiment was originally performed by the psychologist Saul Sternberg in 1969. So here's the data that he collected. And I'll ask you, which algorithm does this pattern look like? What does this look like to you? On the x-axis, we have the size of the set, and on the y-axis, we have the amount of time it took for the person to answer yes or no to the probe. And we see a straight line that is ascending, a linear trend. This really looks like a serial algorithm. It looks like we're scanning each number one at a time, and it takes longer to scan a longer list of numbers in our working memory. You might also notice that this graph has two different kinds of dots. It has positive and negative. What does that mean? What is positive and what is negative in this context? Positive refers to the probe indicating a number that was in the set that the person saw. So if I show you a series of numbers and then I ask you, did you see the number 3? And number 3 was actually present, that's a positive trial. The number that I'm asking about was in the set. Sometimes I'll ask you, did you see a 3? And actually there was no 3 in the set at all. That's a negative trial. There was no 3 present. It seems that these two types of trials are taking about the same amount of time. That's kind of interesting. So that's something that we should get into. Why exactly are positive and negative trials taking the same amount of time? And there's another thing to consider. How does the position of the number in the array affect the search time? It looks like we're using a serial search algorithm. So let's think about that again. The serial search algorithm consists of a few steps, right? Step 1, you have to arrange the numbers in a row. Step 2, you have to scan each number one at a time. So what happens when we find the number? Well, I think it would make a lot of sense if we stopped when we find the number, right? Like, I don't have to keep searching after I've already found the number. That was my goal in the first place. I only wanted to know if the number was present or absent. Once I find it, I don't have to keep looking. That seems kind of dumb and redundant. So yeah, maybe I just quit. If that's true, if the algorithm ends when the number is found, then that means that the search time will be much shorter when the target number appears earlier. So then the order in which the numbers appeared will really matter, right? Because if it's the first number, wow, that's really easy. I just go through the first number in the list and there it is and I'm done. But if it's the last number in the list, I got to go through everything else first, and that's going to take a long time. Well, what if the algorithm doesn't end when it finds the number? This might seem kind of silly and counterintuitive, but it's at least possible. We have to consider the possibility that our search algorithm does something maybe kind of dumb, and even after it finds the number it's looking for, maybe it keeps looking. Like, I don't know, maybe it's just paranoid and has to be sure. It's like, gotta check everything. Or maybe it's just a really automatic process and it doesn't know how to stop. I don't know. We have to consider that possibility that maybe the search continues even after it finds the number it was looking for. So if that's true and the process only ends after it has exhausted the whole list, we'll call that exhaustive search. And if that's true, it doesn't really matter where the probe number was in the list. It'll take the same amount of time no matter what, because you have to go through the entire list every time. We call it exhaustive because it's exhausting all of its options. It's exhausting the entire list, right? Even though it already found the number, it still keeps going through to the end of the list anyways. So we have another subdivision, two more versions of this algorithm. They're both serial algorithms, but one is self-terminating. It ends when it finds the number. And the other is exhaustive. It exhausts the entire array before it stops. You would probably think that the self-terminating option is better, right? It seems way more efficient. And I think that's how we generally program computers to find things. I wouldn't want to program a search algorithm in a computer that searches through everything even after I already found the thing I want. That would seem redundant and pointless. But sometimes the mind does things in strange ways. Sometimes the mind is an inscrutable enigma. Sometimes it doesn't do things in the most efficient way. Sometimes it doesn't do things in the way that we think it should. So it's something that we have to investigate. All right, so our question now is, how can we tell if our brains are actually doing exhaustive or self-terminating search? Well, we know that exhaustive search is going to take longer than self-terminating search, at least on average, because we know that exhaustive has to go through the entire list every time, even if the number appeared early on. But we're going to need some kind of comparison. We need some way of comparing these. This is why we want to think about what happens when the algorithm searches for a number that doesn't exist, a number that didn't appear in the list, a number that is not a part of the search set. So what happens when the algorithm searches for a number that didn't appear in the set? If the search is self-terminating, then those positive trials will be much quicker than the negative trials, right? Because negative trials require you to search the entire array. You don't know that the number isn't there until you've looked at every number and said, okay, well now I know for sure that the number is not here. But if the number does appear, then you'll be able to quit. You'll be able to exit the search algorithm before you get to the end. That's why in a self-terminating search, the positive trials on average are going to be much quicker than the negative trials. But what if the search is exhaustive? If the search is exhaustive, you're going to be looking through the whole set no matter what. You're going to be looking through the whole set if the number was present, and you're going to look through the whole set if the number was absent. So it's going to take the same amount of time. Positive and negative trials are going to wind up taking the same amount of time. So to determine whether we're using self-terminating or exhaustive search, we're going to want to compare positive and negative trials. Remember that negative trials are necessarily exhaustive. That means your mind has to check every item to be sure that the target isn't in there, right? The only way you can know that the number wasn't in the set is if you look through the entire set. You have to exhaust all of the possibilities. So we can compare search time in negative trials to search time in positive trials, trials where the number was present. And we can't track search time by position in negative trials. That's one issue, right? So with positive trials, we can say, well, what position was it in? Was it the first number, the second number, the third number? For the negative trials, that doesn't really exist. It isn't in the set, so there isn't a position to speak of. There is no position. So we're going to need another point of comparison. So what we're going to do is we're going to track search time by set size and then compare between positive and negative trials. Here's how this works. For a given set size, 1 item, 2 items, 6 items, 10 items, some trials will have the target in an early position, and some trials will have the target in a later position. So if search is exhaustive, that means that search times are not going to vary between negative and positive trials. And they're not going to vary depending on where the target is in the string. It doesn't matter if it's first or fourth or 10th. It's the same either way. But if the search is self-terminating, that means that search times in positive trials are going to be shorter on average than the same set size in negative trials. Why is that? Well, in negative trials, 100% of the trials will take the maximum search time. Right? You have to look through the entire array, and you have to do that every time for every negative trial. So it will always take the maximum amount of search time. The positive trials where the target number is at the very end of the array, those will take the maximum search time. But some of the positive trials are going to take less than the maximum search time, right? Because the target will be early, or at least be earlier than the very end of the list. For a set size of 1, if there's only one item, well, that's a really easy set to search, right? There's only one thing to look through. For a set size of 1, positive and negative trials are going to take the same amount of time because there's only the one item. There's no difference. For a set size of 2, positive trials are going to be a little quicker because half of the time it's going to be the first item and half the time it's going to be a later item. Right? So half of the trials are going to take only half as long as the maximum. So the total amount of search time, if you think about averaging all of those trials together, is going to be 3/4 of the maximum possible search time. Because half the time you'll be taking maximum and half the time you'll be doing half of maximum. So you average that together and you get 3/4. For a set size of 3, the positive trials will be even quicker. Because 1/3 of the trials will take 2/3 as long, because it will be the second out of the 3 items in the set. 1/3 of the trials will take 1/3 as long, because it will be the first item in the set. And then, of course, 1/3 will take maximum time, because it will be the third item in the set. And so if you average those together, you get 2/3 of the maximum search time. And then for sets of 4, then it'll be even quicker, because 1/4 of the trials will take 3/4 as long, and 1/4 will take half as long, and 1/4 will take 1/4 as long. And if you average all that together, you get 5/8 of the maximum search time. And it'll get quicker and quicker for each successive increase in set length. So as we increase the size of these sets, the difference in search time between the negative trials, which are necessarily exhaustive, and the positive trials, which may not be exhaustive, is getting larger and larger. There's a larger and larger difference between those two. They are diverging from each other. All right, let's break this down. Here are our predictions. Remember, we considered parallel search. And for parallel search, we had a pretty simple prediction that as the set size increased, that reaction time would probably remain the same. We've already seen that that isn't the case, so we can sort of cross that out. And then we saw serial search. We predicted for serial search that as the set size increased, that reaction time would also increase. And in fact, that is exactly what we saw. But also, serial search subdivides into 2 different options. Serial search could be exhaustive. We might exhaust all of our options. We might exhaust the entire list instead of stopping when we find the number. So for exhaustive search, the rate of increase, right? As the set size increases, the reaction time also increases. For exhaustive search, the rate of increase, how fast the reaction time increases as a function of set size, it's going to be the same for positive and negative trials. Whereas self-terminating search, the rate of increase is going to be greater in negative trials and less in positive trials. Because there's a difference in search time between trials where you find the number and you get to quit, and search trials where you don't find the number, so you don't get to quit. So again, exhaustive search, we're going to see the same pattern, the same linear trend for the positive and negative trials. For self-terminating, we're going to see different linear trends, different patterns, diverging patterns for negative and positive trials. Okay, so what is it? Which algorithm do we actually use? When the mind searches an array of numbers, it scans the numbers one by one. We see that already, that we're using serial search, starting from the first to the last number. And it continues scanning through the whole set even if the target number was at the beginning. So our mental search is exhaustive. We always exhaust the entire list, even if we find the number right away. I mean, doesn't that just seem inefficient to you? Why would our minds do this? Why would we perform search exhaustively? Well, exhaustiveness may have some other purpose than just finding a target. Maybe there's some evolutionary reason, like our brains are just wired to want to double check and be really sure, or maybe we want to find all the instances of something. Maybe this is kind of an unnatural task. How often will you be asked to find something in an array of numbers in your mind? Maybe it's not very naturalistic. Another possibility is that this process is just highly automatic, and once you initiate the search, it proceeds automatically and can't be stopped. And that's really interesting because it implies that search is only partially under our voluntary control. So that central executive system in our working memory model, that thing that oversees the operations of working memory and sensory memory and long-term memory, it might issue some kind of command to our working memory to initiate this search, but then once it issues the command, maybe it no longer has control over how that command is executed. It just operates independently. It's kind of an odd thought to think about different parts of our mind operating independently of each other. But it seems to be the ground level reality for a lot of things going on inside our heads. We don't have total control over everything, and this may be one of those cases. We are doing a weirdly inefficient kind of search, maybe because we don't have complete voluntary control over how that search is actually executed. Let's go over the key concepts from this lecture. This was a pretty self-contained lecture, so we didn't introduce too many new things. We mainly talked about certain operations that we perform in working memory, and specifically we were interested in memory search. We talked about parallel versus serial processing, something that we have seen before, but which comes up again in a different context, in the context of search. And we also talked about exhaustive versus self-terminating search, the idea that when we perform this operation in our working memory, it could perform in an exhaustive manner, where it operates until it has nothing left to operate over, even if it has already succeeded at its goal, versus self-terminating, where once it finds the thing it's looking for, it quits and exits the process. Of course, it turns out that that's not actually how it works in our minds. Of course, the search algorithm is exhaustive and it is serial, which may seem really inefficient, but there may be some reason that our brains are wired this way. That's maybe another question that we have to answer. Why? Now that we know that we do this kind of search, now we have to wonder why. And that's a very different kind of question.